all seen that classic atom diagram, right? Electrons orbiting a nucleus like mini planets circling a sun. That's Bohr's model, and it's probably the first image of an atom you ever saw. It's simple, symmetrical, and burned into every science textbook. But here's the twist. It's not what atoms actually look like. It's more of a stepping stone in our understanding, an oversimplified version that hides a way weirder reality underneath. So, let's dive into how Bohr's model tried to explain the atom and how quantum mechanics completely rewrote the rules. Back in 1913, Niels Bohr faced a puzzle. Why did atoms emit light in specific colors, sharp lines, rather than in a smooth rainbow in a spectrum? Take hydrogen. When you heat it, instead of all colors blending together, you get a pattern, a bright red line, a blue-green line, and two violet lines. It's like the atom only plays certain notes on a piano, never sliding between them. Bohr's solution: electrons aren't free to roam everywhere. They can only sit in fixed orbits around the nucleus, each with its own energy level. When an electron drops from a higher orbit to a lower one, it releases the extra energy as a particle of light, a photon. The energy of that photon is given by Planck's equation, E equals hf, where here, E is the photon's energy, f is the color's frequency, and h, Planck's constant, is a teeny tiny number that sets the size of nature's energy steps. Think of it like a vending machine. You can only buy items in exact price amounts, not random fractions of a cent. Similarly, light can only come in exact packets of energy, never in between. Bohr's model predicted the exact wavelengths of hydrogen spectral lines, and it worked for hydrogen. But hydrogen is simple. Just one proton, one electron. Try Bohr's model on helium or lithium, and it falls apart. For one, the model couldn't explain the very fine structure of spectral lines. How it looks like a single color up close is actually split up into multiple very, very close notes. And in multi-electron atoms, the patterns get messy. It also couldn't explain why some transitions happen more often than others. A transition is just an electron jumping between two energy levels, like moving from the 5th floor of a building to the 3rd. Some jumps are popular and happen a lot, while others are rare. Bohr's model couldn't tell us why. And then came the fatal flaw. According to Maxwell's equations, any accelerating electric charge, like an electron whizzing in a circle, should continuously give off light. That means it would lose energy, spiral inward, and crash into the nucleus in a split second. If that were true, all atoms would instantly collapse. Obviously, this doesn't happen, or... So when Bohr's model hit a wall, quantum mechanics kicked in. In 1926, Schrödinger proposed a radical idea. What if electrons weren't particles on tracks, but waves? He developed the Schrödinger equation, which gives you orbitals, not orbits, regions in space where an electron is most likely to be found. These orbitals aren't simple circles. They're 3D shapes like spheres, dumbbells, and clovers. The square of the wave function gives a probability density, essentially a map of where the electron might be. So instead of a neat loop, you get a fuzzy cloud. Electrons don't have exact paths, they exist in a haze of probabilities. This model, the quantum model, doesn't just sound cooler, it works. It explains chemical bonding, why electrons fill orbitals in specific orders, and why atoms are stable, along with why the periodic table even has its shape. This wave-particle duality is real, and quantum mechanics is the only theory that captures it. So the next time someone shows you that little atom with circles and dots, you'll know better. The real atom is a complex, vibrating probability field. It's governed by strange equations and impossible certainty. Bohr gave us a really great first draft, a necessary chapter in our understanding that the quantum model is a real story. It's weird, it's wild, and it's the closest thing we have to how atoms actually behave. And honestly, that makes the universe way more fascinating.